Right. Here we're just gonna have a quick look at aircraft stability, particularly in longitudinal axis. So analysis of longitudinal stability, that is. Um, First up, gonna have a review of stick-free stability. Before we move on to analyzing an aircraft in a stick-free sense and having a quick overview of the differences between the two in terms of the values we get out. Right, so just very quickly recap some of the basic concepts. Aircraft have 6 degrees of freedom. So we've got 3 axes involved here. As you can see there, we've got the lateral axis, the vertical axis, and the longitudinal axis. The 6 degrees of freedom come from the concept that an aircraft can rotate about each of these individual axes. So we can rotate about this longitudinal axis, pinning the axis from front to back allows the aircraft to roll. Next, we can pin the aircraft about the lateral axis. This will help pitch the aircraft. And finally, if we take it through the gravitational vector, the z-axis, we can yaw the aircraft. Right, so 3 distinct axes, of which we've got 3 moments being produced. If we rotate about each of these individual axes, we require a force. So we require the lift force in the lateral axis to pitch the aircraft. We require a side force, typically to roll or yaw the aircraft. And this produces our moment. So we rotate about the longitudinal axis. We start analyzing the lateral moment. We rotate about the lateral axis. Notice how it's positive through the starboard wing. Will give us the longitudinal moment. And finally, rotation about the vertical axis, where we yaw is and basically the effect of directional stability. Right. Similarly, the other 3 degrees of freedom come from the longitudinal, lateral, and vertical translation. Right, so this is the concept that the aircraft can move in a linear direction. So if we move through the longitudinal axis, it's clearly moving the aircraft forwards. If we move positively in the right direction through the lateral axis, we have a sideways motion. And obviously the aircraft can go up or down in terms of its altitude, hence we have a Z or vertical velocity. The sum of these 3 gives us the overall aircraft speed. Right. When we talk about the aircraft stability analysis, one of the key things we aim for is aircraft trim. Right, so a typical aircraft, analysing most of the forces involved here, shows that we've got the 4 forces as usual. We've got the thrust, the drag, the weight act as the centre of gravity, and the 2 main products of lift, which are from the main airfoil, the wing, and in the conventional one, that being the tail. Right. Typically, the assumption we can make is the thrust vector, although it's not obvious in the diagram, the assumption we can make is the thrust vector, the angle between that and the drag vector is pretty much 0. We can assume they're equal to each other. In trim, if the aircraft trimmed, typically the thrust will equal the drag. We can ignore the total concept of those 2 affecting anything. Now, the main things we're going to look at are the forces perpendicular to our longitudinal axis, which is there. Roughly, right. There's 2 key equations to produce here. There's one where we analyse the moments involved, and we typically do that about the centre of gravity. Get rid of the scribbles. Right, what we can see is There's the center of gravity. Chop the aircraft in half through that axis there, and anything that way is positive. Anything aft of that is negative. Yeah. This main aerofoil is cambered, so it produces its own naturally occurring moments about the center of that, which is the aerodynamic center. So it's automatically got moment there. Right. The rest of it comes from the concept of a moment being a force times a distance. So this lift from the wing is the aerodynamic force, and the distance that we want is this bit here. Right, so based on that airfoil, we can clearly see that is the distance from the leading edge to the center of gravity minus this distance here, which is the aerodynamic center. That will give us the required distance there. Right. Behind the center of gravity, we clearly have a tail section. We've got a lift from the tail, and we have its arm. As we're taking moments from the center of gravity, the arm is this length here, which I'll label as little l, little t. So force, distance. Right. If we talk about trim condition, the moments that we have here will typically equal 0 because if it starts pitching, then the aircraft's going to start to climb, which therefore corresponds it's no longer in trim, it's not straight and level. Right. Our other force is summon the forces perpendicular to the longitudinal axis. Nice and easy this. This is the lift going up. So it comes from the wing and the tail. And let's subtract the weight from that. And obviously, if the aircraft is straight and level in trim, it's not climbing, it's not descending. So these need to balance out. Right. These equations that we see here are going to come back in very shortly. Just have a quick little bit more of a recap of basic principles first. Right, so in fixed stability, we talk about trim condition. You've just seen there that the moments need to sum to 0, and obviously the forces will sum to 0. Right. Scenario: if the aircraft in question, we need to reduce the aircraft speed, but what we don't particularly want is to change the altitude. So it says here the angle of attack should increase. In principle, for positive fixed stability, the aircraft will respond with a nose down or an anti-clockwise moment. Right. Principle of this, there's our lift equation. Afro B squared SCL, so density, velocity squares, area, coefficient of lift. In trimmed condition, that will equal the weight. So at any particular point, we can assume the weight's fairly constant for a short period of time. Obviously, the aircraft is burning fuel, but for a matter of minutes or seconds, we'll assume this is constant. Right, so if that number is fixed, we need to make sure that the lift is fixed as well. Right, if the altitude is to stay the same, we cannot change the density. If we start climbing, the density will usually decrease. If we start descending, obviously the density will be reversed, it will go up. At high speeds, you're very rarely going to start extending the flaps and slots, so the wing area is going to stay the same, which leaves you two things to do. So in the scenario we see here, we slow the aircraft down. The only way we can maintain the same amount of lift is to increase the coefficient of lift. So scenario looks like this. Angle of attack. So you have a typical lift curve slope. You might be at the small angle of maybe 2 or 3 degrees. We have a particular CL value. So just make a number up for this. There's 0.1. Right. We need to increase the coefficient of lift. And you can see this is going to correspond to a new point on our gradient. Away from the stalling point, it's going to correspond to a new x-axis value, a greater x-axis. Now, maybe 4 degrees, for example. So you can see the angle of attack has to increase. The only way the aircraft can respond is pushing the nose down. It changes the pitching value. Right, if we then want to maintain this new slower speed, higher angle of attack, then what the pilot needs to do is adjust the elevator if he wants to start changing other things involved. So this is going to be the concept later on. The elevator is going to come in. Right, the elevator, as we start to change the moment, it's deflected upwards. If we start deflecting the elevator upwards, it's classed as a negative angle. So if we have a trim elevator angle of -4 degrees, for example, it means the elevators have to deflect upwards. It's a little bit against convention, but it's something you need to remember. Right, down here, there's two notations involved. The one that I'm going to go through for this is this symbol here. This is going to be the elevator deflection angle. Right. Moving on, sticking with the static stability stuff, or the stick fixed values. One of the biggest things that you then produce is something called a trim graph. So this is the trim graph for longitudinal stability. There's a couple of key concepts involved. Right, this is going to start to link in what we just said in the last slide. So in the last slide, we said if we slow the aircraft down, so B goes down, we increase the angle of attack. It then said the aircraft's going to respond with a negative moment. So you can see here, if we had our 2 degrees from the previous slide, we had to increase it to 4. You can see we're at the small negative value because this is 0. Higher values, that's a high value. The pitching moment, that's a slightly less positive value of that pitching moment. Obviously, higher angles of attack correspond to a more negative output. Now, key points on this graph. First one, these are all the conditions required for positive static stability in the longitudinal sense. Right, so CMO is the pitching moment, the coefficient of the pitching moment. It's 0 degrees, absolute angle of attack. And note it's above 0, so this has to be positive. This is the whole reason we put a tail section on. So the aerofoil will produce its own pitch and moment. It needs to be balanced out by the tail section. The next bit, notice this gradient starts to decrease, decrease, and decrease. So the next bit is our trim graph gradient has to be negative. Right. And finally, there's 2 points to make about this one. This is the angle at which you will fly the aircraft. It's the trim condition angle. Needs to intersect the x-axis. Now, key bit here is, remember, if we slow the aircraft down, we increase the angle of attack. The angle of trim must fall between the stalling speed angle, Vmax angle. Obviously, if it falls too low, then we'll be exceeding the velocity. If it goes too high, we're probably going to stall the aircraft. Right. Next in the static stability stuff that we've looked at is the neutral point. So this is a key position on the aircraft. Neutral point is classed as a key location on the airframe. Right, so we've just looked at the trim graph that looked a little bit like that. Right. Particularly, this is a key concept. So on an aircraft, there's the main airfoil. Obviously, you'll have the tail section further back. Your neutral point might sit about here. And your center of gravity might sit there. Happy days. Right. As this center of gravity starts to move backwards, the gradient that we see here becomes less negative. So it maintains the origin on the y-axis, but it might move backwards. So you'll find its trim angle starts to move further back to a higher value. So that might sit there. Once this center of gravity has moved to this point, put in line, this trim graph gradient will eventually look like this. It is horizontal. Right, so the neutral point is defined is the location on the airframe where if you move the center of gravity, our trim graph gradient equals 0. Right, you can see that the tail section has a big impact here. Neutral point, aerodynamic center, so that's from the main wing. All of that is the tail section. Right, key things here. H means the locations are in terms of a ratio of the chord length. So, and here for it again very quickly. So, neutral point might sit there. This is just to show you some basic numbers. Our chord length might be 2 meters. That distance might be, I don't know, 1.2 meters. When it's in H form, the neutral point, rather than being 1.2 meters, will actually be 1.2 divided by its chord length. It'll be written like that. So it's basically 60% of the chord length and 0.6 C. That is a ratio of the chord length. Similarly for the aerodynamic center there. Right, the rest of them, we've got the tail section efficiency, a volume coefficient, which I'll talk about very shortly, the lift curve slope, is the gradient of CL against alpha for the respective aerofoils, the stabilizer, tail section, and the main aerofoil. And we've got an impact from the downwash involved as well. Right. This stabilizer volume coefficient is a relationship from the tail. Let's see here. Right. There's our moment equation from earlier on for aircraft in trim. We said that equals no. And remember earlier on, we said force times distance is the moment. The aerodynamic force involved is typically the lift, so that would be a half rho v squared s, its respective coefficient. And the distance involved is the chord length. That will give you the moment. So what I'm going to do is rearrange this so we turn this into a pitching moment. And you do that by dividing by half rho v squared sc. I'm going to do it to every single part of this. Right, I'm just going to jump out of this and show you this a bit clearer. Let's take that. Right, dividing this first part, so the moments about the center of gravity, gives us the pitching moment, the coefficient of that. So that's written as C M, but it's a particular point. So everything just cancels out, gives us a direct moment. And the same thing can happen to this bit here. Divide that by the same thing. And so you take a moment, you divide it by the dynamic force and its respective distance. That too turns into a coefficient. And this similarly is the coefficient of moment got the aerodynamic center. Right. The lift from the wing follows suit. So when you take that and divide it by half rho v squared SC. Right, so plus this is pretty straightforward what's going to happen in this sense to some extent. The lift force, when you divide it by a half rho v squared s, it instantly turns that to a coefficient. It's rearranging the lift formula effectively. So half rho v squared s divides that, turns it to the coefficient of lift. Obviously, in this case, it's going to be for the wing. This C value, this chord length, is dividing the distances. And sometimes written like that, with a little bar above it. But if you go back to what we just said about the neutral point, if it's got a line above it, it's in terms of the chord length now. So it's our H value. So the center of gravity will be written just as H. That is the HO from the neutral point. And obviously, similarly, you can get the neutral point as HN as well. Finally, the lift from the tail is a little bit more to this one. I'm going to write this out a bit clearer. The lift from the tail is the lift equation again. Right, and the key bit here is it's the area involved is that of the tail, and the coefficient lift will be that of the tail. Multiplying that by its arm length. On the bottom, we've got half rho v squared s. And the key bit here is the area involved was the wing. We've got the chord length. What happens here is we've got half cancelling half out. Density cancels out. It's typically roughly the same velocity over the main wing as the tail section, so that's safe to cancel out. Right, the areas are totally different. And it's this bit, if you ignore the CL value, it has a particular definition. Now, the area from the tail multiplied by its arm divided by the area of the wing times the chord length of the mean aerodynamic cause is a volume ratio. If you think about it, we've got meter squares times a meter. And again, the bottom meter squared for the area, meters for the chord length. So meters cubed, it's a volume effectively, but obviously it's a ratio. Right. Now, our final equation, if we jump back into our slides, is written like that. Right, so the pitching moment about the center of gravity is the moment about the aerodynamic center, the coefficient lift of the wing, multiplied by its distances in terms of the chord length, minus the tail section and the tail volume. Right, example coming up here. Handful of key formulas that we're going to look at I might need. Again, most of these you've just been through. So there's the tail volume. There's our neutral point. There's our pitching moments. There's our coefficient version of that. We've done the lift care slope, which was the rate of change of CL against its angle of attack. You can see it's rearranged in that form. The only two left to talk about really here are the trim graph, effectively the neutral point equation, times its trim graph gradient, its lift care slope gradient rather. And this one we're going to see a little bit later on is relating to the elevator section. So to trim the aircraft out using the elevator, CMO from the trim graph, its gradient of that particular trim graph, our angle at which we have to set the aircraft to, there's VH, and then we've got a relationship of lift to elevator. So this is, I'll talk about this again later on. And finally, this is taking an angle of attack to an absolute angle of attack. So effectively shifting the lift care slope over. Right, here's our example. quickly with that. Right. We can see we've got a wing body. So this first bit there tells you the wing body is just the fuselage and the wings. There's no tail section yet. Typical method of how you start the design an aircraft. Make sure you're happy with what you've got. You need the tail section to fit based on the stability that you want. Right, it says when the geometric angle of attack is minus 1.5, the lift's bound to 0. So just going to make a quick sketch of this first. This first bit of information talks about a lift curve slope. Right, roughly looks like that. The first bit we get told is at minus 1.5. And minus 1.5, we can see that CL is 0. Intersects the y-axis down at 0, minus 1.5. We increase it to 5. It's now up to 0.52. Right. Similarly, you get a little bit more information about the pitching moment, about the center of gravity, based on a couple of angles. But the first thing I'm going to do is work out this gradient. All right. The gradient A corresponds to the change in the lift, the change in the angle of attack. And it's just the standard gradient formula. A location on the y-axis, a second location on the y-axis, divided by those corresponding points on the x. Right. Y2, make this point 2, make this point 1. So y2 on the y-axis, you can see, is 0.52. You're going to subtract 0.1, which is 0. x2, so on the y-axis for 0.2, you can see if you read that along and down with phi. And this one is at minus 1.5. Right, so the lift curve slope here is in the calculator with that. About 0.08. Right. The question asks you to calculate the location of the aerodynamic center. So what I'm going to do is take the pitch and moment equation, except for the tail section here. So pitch and moment is about the center of gravity. Is that about the aerodynamic center? Plus the coefficient lift of the wing. And remember we said this was XCG minus XAC. I put this in chord length methods. H for center of gravity. HAC for the aerodynamic center. And what I'm going to do is I'm going to put the respective values in for one angle of attack and the same thing for the other angle we get told. Right, key points, CL is rearranging this effectively. So the CL is basically the lift curve slope times its angle of attack. Right. First set of values then is when the angle of attack is 1 degree. So if you read this here, as the angle of attack increased, you read the coefficient of moments about the centre of gravity. So at 1 degree, CMCG is minus 0.01. You're going for the moments about the aerodynamic centre. Right, obviously this is now substituting alpha and A for CL. So we've got the angle is 1 degree. We need this in terms of the absolute angle of attack. So this is going to be the geometric angle plus the angle required to basically shift this lift curve slope to 0, which requires adding 1.5 degrees. A, you can see we worked out there is 0.08. Right. H, remember, is the center of gravity, which is 0.35. We need the location of the aerodynamic center and its moment. So again, we don't know HAC. All right. We can do exactly the same thing, but for the other set of data, 7.88 degrees is 0.05. Right, so same two unknowns is now 7.88. Same lift curve slope, so it's still going to add 1.5 degrees to it. In terms of by its gradient, that's 0.35. That's HAC. Right. Hopefully you can see we've got a simultaneous equation. Doesn't matter which way you go, but you need to eliminate one of the unknowns. Arguably, the easy one to do is to eliminate this because CMAC is the same value, if you like. You've got 1 multiplying both of them. So I'm going to subtract these two equations. Minus 1, 0.01 rather. Subtract 0.05. Give me 0.06 is negative. Whole point is they cancel out. Right, just do the working out that we need. The rest of it. So 7.88 plus 1.5. Then multiplied by 0.08. And 504. And similarly, 1 plus 1.5 is obviously 2.5 times that by 0.08 is bang on 0.2. All right. If you subtract 0.2 minus 0.7504, we get minus 0.5504. multiplying our brackets. We can't touch that just yet. Right, and this is just simultaneous equation theory here. So divide through by minus 0.5504. Easier with 0.35. Take away HAC. Right, so HAC, it's because that's minus, needs to go to the other side, but I'm going to bring all this over here. So we're going to get 0.35 minus negative 0.06 dividing negative 0.5504. Right, that should give you, in terms of the chord length, the aerodynamic center to be 0.241. Right. The other one that needs is its coefficients. We get minus 0.01. It's just substituting this back in. Either equation. Oh, oh, that is now 0.241. If we take all of that to the side by subtraction and work it out with minus 0.01, we get our coefficient value. Right. Jump back into this. So the rest of it just comes from the respective formulas here. So it then says, with the addition of a tail, we get a new CMCG value to consider, but it's now just, is it stable? Right, here we go. So stability is analyzing the key concepts from the trim graph that we discussed. So firstly, with its gradient, you find everything's been calculated there. The only thing you need to work out is its tail volume. AW is our lift curve slope we've worked out. That's our 0.08. We just got these values. So the center of gravity was 0.35. The aerodynamic center is what we just worked out. BH, as you can see, so the tail area, its arm, wing area, the chord length, all multiplied together gives us 0.34. AT being the lift curve slope for the tail, you can say that's 0.1. Gets given in the initial data, along with our downwash. So trim graph gradient is negative 0.133. Right, negative is one of its criteria, but again, we don't know its CMO value just yet. So that means if you were to plot a graph of this initially, we don't know, if we know it's negative, it could look like that, it could be there, it could be there. But as soon as it goes under like that, CMO is now negative. Obviously, it's losing one of its criteria. Right. Other measures is neutral points. A lot of this is just a repetition from the previous slide. So you can see this is effectively the neutral point equation with one minor adjustment. Aerodynamic center, we just calculate as part A. Everything else is given to us. So we've got the tail volume again, we've got the tail efficiency, the two lift care slopes, and our downwash. In go all our numbers. Neutral point is 0.517. And when we consider that with the center of gravity, only then can we make a comment. So this is a particular location. This is where the trim graph gradient will equal naught. But the neutral point then becomes the important bit with the center of gravity here. So neutral point 0.517 minus the 0.35 for the center of gravity. The static margin is positive, and that is our criteria for positive longitudinal stability. Right, some of these values are going to come back in shortly once we have a discussion of stick free concepts. Right, stick free, clues in the name. When the aircraft's in steady level unaccelerated flight, the control column is let go by the pilot. This lets the tail section do as it wishes, so it's going to start floating against natural aerodynamic forces. Obviously, what it wants to do is produce restoring moments to balance everything out. Only once everything's balanced is the point of trim in this sense. Right, two things affect the stick free. Starting with a little scenario here. Right, in stick free, here's the space diagram is our starting point. Right, in stick free, the elevator is allowed to rotate about its horizontal axis. The pilot doesn't touch it, so it can do what it wants. The airfoil that we've got in front of us is symmetrical. Right, often the typical application for most aircraft is for the tail area. Right, best thing that affects this is say there's two things. The first one is going to be the angle of attack, which is what we see here. So it's symmetrical. So when the elevator is at 0 degrees absolute angle of attack, your lift care slope will look like this. Angle TL. It will go through the origin. So when it's at 0 degrees, it produces no lift. Right. First thing I'm going to do is increase the angle of attack of this airfoil. There we are. You can see that by increasing the angle of attack with respect to its incoming airflow and its chord line, we get a new angle. This affects the pressure distribution over the elevator section. So what's going to happen is if you see, because of this pressure distribution, initially, whilst the elevator section is at 0, so this section here tells you the elevator section is currently 0 degrees, but the change in pressure will produce a change in lift, which wants to start to balance the aerodynamic forces out. So we get an imbalance. First thing the elevator is going to want to do is it's going to want to push upwards, right? So just jumping back. This elevator is going to want to go from this red position to something that looks like that now. So it's moved upwards. Obviously, it's not a great diagram, but it's attached to this full section. It's moved up. You can see it's increase in its angle. So delta E is now no longer 0. Right. If it's moved up based on what we said, that will be a negative angle. But in this instance, it will have dropped to a number less than 0. Right, so that is one instance. That's just a quick explanation showing you that by increasing the angle of attack, we need a new elevated deflection to balance the forces out, trim the aircraft back to how it was to restore the moment. Right. Alternatively, we can have a second scenario. So this time, rather than changing the angle of attack initially, the elevator changes. Right. If the elevator changes and the angle of attack stays constant this time, we again introduce another pressure distribution or pressure imbalance requiring aerodynamic forces. Basic theory will tell you low pressure on top, the high pressure on the bottom. First thing it's going to want to do is produce an upward slip force like that to balance everything out. Right, here's the concept. Scenario 1, we held the elevator constant initially, but allowed the angle of attack to change. So what's happening is we're changing the value of CL. It's partial because it's changing CL by only allowing one of the variables to change. And in that first scenario, we were changing only the angle of attack, the absolute angle of attack, depending on what you've got. Right, and its response is just new angle. In this particular scenario that we've got here, where the elevators had to move, but we've got a fixed angle of attack. So this time, the change in the lift, so the change in the hinge moment, we want to look at it for the tail section, is allowed only the elevator to move. We're only considering one variable, hence the partial sign. And that's going to respond by producing a particular deflection. Right, so there's two distinct variables here: the angle of attack of the tail section or the elevator angle. Right, that will produce our overall moment. Right, if you look what we've got then, what's going to happen in both of those instances is this aircraft is then going to want to achieve equilibrium. It's going to want to balance out. As soon as an imbalance in one of the angles, it will produce a pressure distribution, imbalance the lift, which will eventually restore a moment. Right. It will then aim to achieve equilibrium or balance. In that condition, these need to sum to 0. That is for trim or balance. Right. Typically, rarely to change the angle of attack. It's this bit that's allowed to change. This is allowed to do what it wants. It's often denoted as the free elevator because it's free to do as it wishes, a clue's in the name. Right, so this formula will slowly get modified. like that. So basically the same condition. The moment we need is trimmed. It's affected by either the angle of attack or the elevator. And if the elevator is free to do as it wishes to balance this out, the angle that we set this to is denoted the elevator free angle. Right. Typically, it's the elevator that does the job. So what we can do is decide an angle for this. And we can very quickly rearrange this equation to determine the elevator deflection. Right. If you think about this elevator angle is currently getting multiplied by its respective hinge elevator value. So the first thing we need to do is divide through by this relationship, this differential or partial. So what I'm going to do is rewrite this equation just exactly as it is. I'm not changing anything just yet. Just make it a little bit easier to explain what's happening. So you've got the elevator hinge moment, the trimmed condition, is the elevator gradient with respect to its angle of attack. So that is this bit initially. Right, and divide through by this bit, which is the elevator hinge moment based on the elevator deflection angle. And so in that format, it's a little bit easier to see. So it's dividing through the angle of attack is currently sat there as a multiplier. And then you're going to add this bit. Right. All we need to do is, because we want this bit on its own, need to determine the angle required for trim in sec-free sense. All of this over here is going to get subtracted. So this is what you're going to see in the next little bit. We're just subtracting everything, otherwise sticking the minus sign in front of it. The elevator deflection required for stick-free stability is as we see it there. Right, these values whichever way you look at it, the numerator and the denominator are basically gradients of graphs. So you'll be plotting the hinge moment against the angle of attack. That one is typically negative. And you can plot the elevator deflection against the hinge moment. See, it is partial because they're the only two things involved here. Again, that one's negative. Right, so that means we've got minus sign there. That answer or value is typically negative. That one's typically negative. So the concept here is a positive tail angle, that you can see in the diagram, produces a negative elevator deflection. So for positive angle of attack, you're going to end up with a negative elevator deflection, which means it will have to deflect upwards. Right. This elevator concept then is going to come back in a little bit of a naughty sense here. In the stick fix stuff that we looked at earlier on, we had coefficient Mitchell moments about a center of gravity is that of the aerodynamic center, lifting the wing. This isn't the important bit just yet. XCG, XAC. Right. We then subtracted LT, sorry, coefficient of lifts rather. And its arm. Right. The bit that I'm going to focus on only here, only, is this coefficient of lift from the tail. Right. Coefficient of lift, it's part of the lift curve slope. Quick reminder, CL, this is for the tail only. A little bit like that. It will have its own gradient, and at a particular value, it will have its own angle of attack. So CLT, the coefficient lift for the tail, can be written in terms of the lift curve slope. Remember, A is the gradient. At this particular angle, so that gradient at that particular angle will give you its CL. Right. We then introduce the fact that the CL value can change based on the elevator deflection. That basically is the angle of attack part, only obviously it's fixed in this sense initially. And based on the theory we've just been through, it was no longer just the elevator deflection we had. We had a particular point which was labeled as the free elevator deflection. So we can then come to make a substitution for the free elevator deflection that we had here. So these two hinge gradients are the hinge moment on the angle of attack, the hinge moment of the elevator with respect to the fixed angle is going to get substituted into here. So as I said, a little bit naughty, but it shows us the overall effect of the lift on the tail. Lift curve slope at a fixed angle. ACL behind the elevator deflection. So obviously its lift curves can change based on changing our hinge, our elevator. And the angle that we set that to, I've just said based on the last bit, was the minus value of the first moment, hinge moment, was based on the angle of attack. The second hinge moment, which is based on elevator, multiplied by the angle. Right, so alpha t means our trim point on that. Right. To show you these on the PowerPoint, there's a small change to show you. So there's our formula. If you notice, I'm now introduced a small modification because we've let the elevator move free. The CL value that we just had in that proof there has an apostrophe. That is used to designate that we've got stick free value. So this coefficient of lift is only for stick free. And the apostrophe will only sit on the tail section because obviously there's no stick free elevator on the main area for the main wings. Right. The rest of the formula that we've seen in part 1 can then get modified based on something called the free elevator factor. So we introduce something called the factor of stability, which is 1 minus tau, where tau is as you can see here, right? There's various things involved. There's more typos while I was checking, right? This is not alpha t, it's supposed to be AT for clarity. Well, that is the lift curve slope of the tail section. Right, so tau 1, so going to be 1 minus 1 divided by the lift curve slope of the tail. The change in the lift from the elevator value. And our two hinge moment derivatives that we've seen. Right, so the coefficient lift for the tail. See, most of this was involved. Introduces the stick free elevator factor. Right, it's just a multiplier effectively, this that modifies the numbers. To show you how the rest of these equations change that we've seen then. So this is the general pitching moment formula. Aerodynamic center, lift from the wing, lift from the tail, tail volume. Modifying it into stick free, you can see nothing happens to the first section. The wing only happens to the tail section, introducing the stick free concept of CLT or the free elevator factor. Right. There's one more modification for CMO, and then it's the other formulas we've seen from earlier on. Nice and easy modifies this. So CMO, this is a previous formula that I've introduced in other videos. Coefficient moment at the aerodynamic center. There's our free elevator factor, VH again. Angle for the tail section, angle of attack. Tail incidence, and the downwash. Right, the rest of them, neutral points, and our trim graph. Basically, the formulas aren't changing too significantly. It's just working out what the F value is in this. Right. Quick example to show you to finish this off. This relies on the values from part 1 because, as you can see here, it says a full-size version of the model in question 1. So some of the values that we've already calculated will be needed here. Back into the whiteboard. Right. Full-size version of our aircraft from part one is constructed such that most of the aerodynamic design features are maintained. So this is the whole point of making the model, scaling it up. Most of the coefficients will still be the same value. Right. Full-size aircraft has a wing area of 19 meters squared, with a weight and an elevator control effectiveness. So it says taken CMO as 0.06. What is the elevator deflection angle? Right. Elevator deflection angle is CMO. Oh, the trim graph gradients. It's trimmed angle of attack, tail volume, and in this case, it's CLT divided by. All right, if I label these up, where the numbers are going to come from. CMO, you can see in to where. The trim graph gradient was worked out in part 1B. It was the first part we done. Alpha N, our trim point, we need to work out. So I'll put a question mark over that. VH is worked out in part one. Again, it's the same aircraft, the same ratios, it's just scaled up. So VH will be, again, from 1BI. Finally, this change in the lift because of the elevator deflection is the elevator control effectiveness. I just put EC for that. Elevator control effectiveness. Right, so we've got one thing to work out, and alpha N comes from finding what CL is, linking it to the trim, the lift care slope, and basically coming back to that. So over here, 2 minutes, we've got define CL. We know the lift care slope. We know what the tail section is made up of. We need the value of CL to read the alpha angle. So CL is the lift value, the trim. So lift equals the weight. Right, values. You can see all of these are going to come from the question. We've got a weight of 2.27. The density is this is getting flown at sea level. That's in metric. That's 1.225. I'll get that from the ISA table. We've got a velocity, 61. And a wing area of 19. Right, so our CL is 0.524. Right, what that means now is there's your coefficient lift, there's your angle of attack. We know this point here is 524. We also know we've got rate of change of 0.1 from earlier on. The tail section, verify that number. Sorry, this is the main one, so that's 0.08. So this was what we calculated at the very, very start, the very first thing we calculated in part 1. Right. You know those two, you can do y equals mx plus c if you wish, or you can do the relationship. If you know those two, you should be able to get that point, which mathematically tells you the trim angle is CL over the lift curve slope, or 0.524 over 0.08. Right, what I'm going to do, plug all those numbers in, and we will get our elevator deflection. Same old 0.06 straight from the question of trim graph. Angle on the bottom, tail volume from earlier on. The elevator control effectiveness gives you the elevator deflection, which is, in this case, minus 1.94. Right, might very easily be asked, what does that mean? A negative value tells you it has deflected upwards. Right, the rest of the values, I'll go back to the PowerPoint and very quickly explain where these are coming from. So it says, assess the stick-free static stability of the aircraft based on our hinge moment derivative. So these are typically negative and very small. Right, first off, obviously you have to work out our stick-free elevator factor, or F. 1 minus DCL over DE. So this is our elevator control effectiveness, straight from the question. Alpha T, straight from the question data. Our hinge moments with the two negative values that you've just seen there, and that gives us our F number of 0.754. Right, I'm going to use that to work out everything else. Right, so CMO 0.037. It's basically plugging in some numbers into our formula now. It's positive, so it's still one of the indicators that we've got positive stability, although it's stick free this time. Our usual point. This is again just plugging numbers in. You'll see a lot of these are the same values from earlier on as well. Aerodynamic center doesn't move. Tail volume, our lift curve slopes, our downwash, just basically get multiplied by F effectively. So that is 0.448. Right, static margin. Same principle. Our new stick-free neutral point, man, the center of gravity. It's still positive, although slightly less, so it's still indicating positive stability. And finally, our trim graph. All right, a couple of things I want to do to finish off. That is the analysis of the values. First thing I'm going to do is, numbers-wise, the stick-free moment at 0 degrees absolute angle of attack, or CMO. the stick free value for the trim graph now is 0.078. That's negative. Right. You can construct the trim graph for this. And so CMCG alpha A, we know that point there. We know it's gradient. Right. So we've got two things. You've got, if you think of the straight line, we know it's going to be a straight line. Y equals mx plus c. Right. In this instance, what we actually have on the y-axis is CMCG. M is that. The x-axis is alpha A. And we know it's intercepting the y-axis at positive, not 0.37. Right. If we want to trim our aircraft out, we can find a particular point of intercept. What that will be for stick free. Right. And that occurs when the pitching moment, if you're going for this point here, this is just a generic point for now. We're going for that point there. We know on the y values that is 0. Right, so we're going to go 0. We're going to rearrange this for our trim angle or alpha A. So that will say 0.0037 is now negative. We'll go up here and divide through by, right? So we've got minus 0.0037. Divide all of that by minus 0.0078. That will give you your alpha A. Now, obviously, in this case, it's a very substantially small number, but it's the concept of, right, arduous, you'd be able to work out that point there. Right, I say, something you might be able to do. The final point to make on all of this, you probably realise on the walkthroughs that we've been doing, all these numbers are slowly moved less stable. It's pretty common. The stick fixed values are higher than the stick free. But in terms of analysis, it's something you have to do as an aircraft designer. And it's also something you might want to do to make sure that when the aircraft goes stick free, you don't go from being a stable design to unstable design. Obviously, you can see it's very close to doing that in this case. We've got the static margins very, very close to 0. So our neutral point has moved backwards. All right, that does end this particular session.